A user types a username. You need to check if it exists. Easy, right? Until you have 100 million users. Then that tiny question becomes a system killer. Every single sign-up fires a database query. Now multiply that by thousands of requests per second. Congratulations. Your database is now on fire, and your users are staring at a loading spinner. Option 1. Just query the database. 100% accurate. But your latency goes through the roof. Your I/O is crying, and at high traffic it scales about as well as a chocolate teapot. Option 2. Throw it in Redis. Lightning fast, and your database can finally breathe. But storing 100 million usernames in memory? That is going to cost you. Hope you're ready to sell a kidney. What we actually need is something fast, tiny on memory, and scales to billions. Enter the Bloom filter. A probabilistic data structure that sounds made up, but is absolutely genius. A Bloom filter does not store actual data. It stores fingerprints. You hash each username with multiple hash functions, then flip the corresponding bits to 1. When checking if any bit is 0, it is definitely not there. If all bits are 1, it probably exists. Notice the word probably. Why multiple hashes? Hash functions output massive integers. To fit them into our tiny array, we use modulo division. But here's the problem. Different usernames can hash to the exact same index. This is a collision. By using multiple independent hash functions instead of just one, we drastically reduce the chance that two different users flip the exact same set of bits. Time for some spicy math. You need 3 numbers: n, the expected elements, m, the bit array size, and k, the number of hash functions. The optimal k is m over n times ln2. False positive rate p equals 1 minus e to the negative kn over m, all to the power of k, and the bit array size m equals negative n ln p over ln2 squared. If that made your brain hurt, don't worry. There are calculators for this. Let us look at a real example. 1 million users. We want a 0.1% false positive rate. Plug that into the math, and our array size m becomes 1.7 megabytes. We need about 10 hash functions, 1.7 megs tracking a million items. That is insane efficiency. Here's the catch. Bloom filters can have false positives. It might say, yes, this username exists, when it actually does not. But it will never say no when it does exist. One direction is always correct. So in production, you combine both. Bloom filter checks first. If it says no, you're done instantly. If it says maybe, then you query the database to confirm fast path plus safe path. That is how you build systems that actually scale. Database for accuracy, Redis for speed, Bloom filter for insane scale, tiny memory, massive throughput. Hit subscribe if you want more engineering content like this.